Chunking is one of those topics that looks straightforward in documentation and genuinely difficult in production. The theory is clean. Split your documents into manageable pieces, embed them, retrieve the relevant ones. The reality is that your documents are not clean, and the tools that promise to handle them have significant limitations most tutorials never mention. This lesson is the honest version. We will cover what actually breaks, why it breaks, and what the current state of tooling can and cannot fix. If you have ever wondered why your RAG system retrieves technically correct chunks that somehow miss the point, this lesson is where the answer starts. Before going deep on chunking, it helps to see where it sits in the overall picture. A RAG system has 5 stages. Documents come in, PDFs, Word files, web pages, whatever your source material is. Those documents get split into chunks. The chunks get converted into numerical representations called embeddings. When a user asks a question, the most relevant chunks are retrieved. And finally, those chunks are passed to a language model to generate the answer. The orange step, chunking, is where this lesson focuses. It sits at the very beginning of the pipeline, which means any problem introduced here propagates through every stage that follows. Bad chunks produce bad embeddings produce bad retrieval, and bad retrieval produces bad answers, regardless of how capable the language model is. Every tutorial on RAG shows you the same picture. You have a clean document, you split it by paragraph or by a fixed token count, and you get 3 neat chunks, each containing one coherent idea with clear boundaries. The left panel here shows the input, well-structured prose with logical paragraph breaks. The right panel shows the output, 3 chunks, each labeled, each self-contained. It is a satisfying diagram.
The problem is, it describes a document type that almost never appears in real enterprise or research workflows. The warning at the bottom of this slide is the most important text on it. This model works on Wikipedia articles, on well-formatted blog posts, on carefully authored documentation. Your actual documents, the PDFs, the slide decks, the scanned reports, are a completely different challenge. That is what we look at next. Real document collections are a zoo of formats, each with its own set of structural problems. PDFs are the worst offender. They were designed for printing, not for machine reading. Multi-column layouts, scanned pages with no text layer, tables that span pages, headers and footers that bleed into content, all of this is common in research papers, annual reports, and contracts. PPTX files have text scattered across shapes and text boxes in an order that makes visual sense on screen, but is completely arbitrary when read programmatically. DocX files come with footnotes, track changes, nested tables, and embedded objects that chunkers rarely handle correctly. HTML pages from the web mix article content with navigation menus, cookie banners, sidebars, and footer links. Scanned documents may have no text layer at all, producing either empty chunks or garbage from a low-quality OCR pass. And code files have no natural paragraph boundary. A function split mid-body across 2 chunks makes neither chunk usable. The practical implication is that before you can chunk, you almost always have a document pre-processing problem to solve first. The reason chunking deserves this much attention is simple. It sets the ceiling for everything that follows. The bar chart here illustrates the propagation effect. When chunking quality is poor, shown at around 40%, embedding quality is similarly constrained, because you can only embed what you extracted. Retrieval relevance drops further, because the embeddings do not accurately represent the original content. And by the time you reach the final answer, the language model is working with context that was already degraded 2 steps earlier. No amount of prompt engineering or model capability can recover information that was lost or corrupted during chunking. Teams often spend weeks tuning their retrieval logic or swapping embedding models, only to discover the real problem was upstream in how their documents were processed. The red box at the bottom captures the practical implication. The quality ceiling is set at step 1, and it cannot be raised from downstream. The contrast here is stark, and it is not exaggerated. The left panel shows the ideal output, one coherent sentence with a financial figure, clear year-over-year context, and a geographic reference that makes the number meaningful. A retrieval system can match this chunk to a relevant query, and the language model can use it to give a precise answer.
The right panel shows what actually comes out of a typical PDF annual report. The number 4.2 appears, but it has been separated from its units. The 12% figure is there, but with no indication it is a growth rate. The page reference, confidential, page 14 of 52, has been injected from the footer. 2 columns have been merged, so continued from previous column appears mid-chunk. A figure caption and an appendix reference are embedded in the text. When a user asks about Q3 revenue, the retrieval system may surface this chunk because it contains the right numbers, but the language model receives garbage context and either hallucinates the missing details or produces a confused answer. Layout failures happen when the chunker processes a document based on its physical or storage structure rather than its logical reading order. The first example covers PDF multi-column layouts, which are extremely common in research papers, financial reports, and academic journals. A naive parser reads left to right across the full page width, interleaving sentences from column A and column B into a single incoherent string. The second example covers PPTX files, where text lives in floating boxes that were placed on the slide in whatever order the author happened to create them. The extraction order follows that creation sequence, not the visual reading order a human would follow. A slide that reads title, then body, then caption on screen might extract as caption, title, body, depending on when each box was drawn. The third example is one most practitioners overlook entirely: rotated or sideways text in PDF sidebars and margin labels. These are simply skipped by most parsers, meaning key terms that appear only in a sidebar annotation are silently absent from every chunk. The practical choice when dealing with complex layouts is to validate extraction output visually before trusting it in a pipeline. Structure failures are perhaps the most damaging category because they destroy the relationships between pieces of information that give data meaning. Tables are the clearest example. A PDF table with row and column headers contains dense relational information. The value 42 in row Q1 and column revenue only means something because of those headers. When a chunker flattens the table to plain text, the headers are often lost and the numbers become a meaningless sequence. The language model receives numbers with no context for what they represent. Footnotes in docx files cause a different but equally damaging failure. A footnote reference in the body text, the small superscript number, gets stripped, but the footnote content itself gets injected inline, sometimes mid-sentence. Statistical qualifications, source attributions, and legal caveats all end up embedded in the main text in the wrong location. Nested lists are flattened to a single sequence, destroying the parent-child relationships that indicated which sub-items belonged to which category. The practical implication is that for any document containing tables, footnotes, or hierarchical structure, standard chunking strategies are insufficient on their own. Noise injection failures are insidious because they do not obviously break the chunk. The chunk still contains real content, just contaminated with text that should never have been included. PDF headers and footers are the most common source. Every page of a corporate report typically carries the document title, a confidentiality notice, and a page number. A chunker that does not explicitly strip these will stitch them into content chunks wherever a page boundary falls mid-paragraph. The retrieval system then treats those boilerplate phrases as content, and queries that happen to match on annual report or confidential retrieve the wrong chunks entirely. HTML pages from the web are even noisier. A typical article page contains navigation menus, cookie consent banners, related article links, advertisement labels, social sharing buttons, and footer content, all of which get mixed into chunks alongside the actual article text. docx track changes are particularly dangerous because the deleted text is invisible to a human reader opening the file normally, but it is still present in the underlying XML. A chunker that reads from the XML without filtering track changes will include sentences that the author explicitly decided to remove, potentially introducing contradictions into the retrieval index. The practical choice for all three of these is pre-processing. Strip headers, footers, navigation, and track changes before chunking, not after. At this point, teams usually face a reckoning. They built a RAG prototype in a weekend using clean sample documents. It worked. They moved to production, and suddenly retrieval quality dropped sharply. The diagnosis almost always points to pre-processing. The statistic on the left is not precise, but it reflects what experienced practitioners report. Roughly 60% of the real work in a RAG pipeline is document preparation, not model selection or retrieval tuning. The 4 items on the right break down what that preparation involves. Stripping noise means removing headers, footers, navigation elements, and boilerplate before the content ever reaches a chunker. Recovering structure means converting tables back into a format that preserves row and column relationships and maintaining list hierarchies. Handling images means running OCR on scanned pages and extracting meaningful text from figure captions and diagram labels. Normalizing formats means dealing with encoding issues, inconsistent whitespace, special characters, and formatting artifacts that differ across file types. None of this is glamorous work, and none of it appears in the tutorials. But skipping it is why so many RAG systems disappoint in production. The tooling landscape has matured significantly in the past 2 years. 5 tools now stand out as the serious options for production RAG pipelines. Unstructured has the broadest format support, over 30 file types, and was purpose-built for RAG workflows with multiple chunking strategies. It is worth noting that some practitioners report quality has dropped in recent versions, so testing on your specific document types is essential before committing. LlamaParse from LlamaIndex is currently the most convenient option for complex PDFs, particularly those with embedded tables and images. The limitation is multi-column layout handling, where text from adjacent columns can be interleaved, the exact problem we saw in the layout failure slide. Docling from IBM Research is a compelling open-source alternative with AI-powered layout detection. It handles tables well, but lacks support for handwritten content and some advanced form types. Reducto claims up to 20% higher parsing accuracy on real-world documents and has strong citation tooling for audit workflows, but cost at scale is a consideration. Marker PDF handles multi-column layouts better than most, but is weaker on tables. The practical choice is not to pick one and commit. It is to test 2 or 3 on a representative sample of your actual documents before making a decision. The honest answer to how far tools have come is significant progress on the easy cases, limited progress on the hard ones. The green column on the left covers what is now largely reliable. Plain text PDF extraction works well. Single column layouts, the kind that appear in most blog posts and simple reports, are handled cleanly. Basic table detection has improved substantially, particularly in LlamaParse and Docling. Standard docx and HTML parsing is solid across all the major tools. The red column on the right is where the problems remain. Multi-column PDF layouts are still the most common failure mode, and no tool handles them reliably across all document types. Merged and borderless table cells, common in financial and legal documents, continue to confuse extraction logic. Scanned documents with mixed content, where some pages are text-based and others are image-based, require hybrid OCR strategies that most tools do not apply automatically. And PPTX reading order remains essentially unsolved. The tools extract text in creation order, and there is no standard way to infer intended reading sequence from the file structure alone. The yellow verdict at the bottom is the most important takeaway from this slide. The tools have genuinely improved, but if your document collection contains the hard cases, you will still need custom pre-processing logic that no off-the-shelf tool currently provides. After understanding all the ways chunking can fail, the natural question is what experienced practitioners actually do differently. 3 practices consistently separate teams that ship reliable RAG systems from those that keep debugging retrieval quality. The first is to sample and inspect before building. Before writing a single line of pipeline code, extract 20 to 30 representative documents from your actual corpus and look at the raw chunks that come out. Not the first 10 pages of a clean example document, the messy ones, the scanned ones, the multi-column ones. This inspection step catches the most serious issues immediately and shapes every subsequent decision. The second practice is pre-processing before chunking. Rather than feeding raw files into a chunker and hoping for the best, practitioners strip headers and footers, fix encoding issues, and handle tables through a separate extraction path that preserves their structure. This is plumbing work, but it is the work that makes the rest of the pipeline reliable. The third practice is benchmarking tools on your actual corpus, not on vendor demos. Every tool performs well on the examples in its own documentation. The question is how each tool performs on your specific mix of formats, layouts, and content types. The green note at the bottom is the most important mindset shift. Pre-processing is not a shortcut you skip to save time. It is engineering work, and it deserves a place in the project plan from the start. This lesson has focused on the pre-processing problem, the work that has to happen before chunking can even begin. The next lesson in this series takes up where this one leaves off, assuming your documents are clean, and examines the 3 core decisions that determine chunking quality. The first decision is chunk size. How many tokens to include in each chunk? Too large and the embedding captures too many ideas at once, diluting retrieval precision. Too small, and individual chunks lose the surrounding context needed to make them useful. The second decision is overlap. How much content adjacent chunks should share. Without overlap, an idea that spans a boundary between 2 chunks gets split and may never be retrieved as a whole. The third decision is strategy, whether to split by fixed token count, by semantic similarity, or by document structure like headings and sections. The right strategy depends on both the type of document and the kinds of queries your users will ask. These 3 decisions interact with each other, and with the pre-processing choices made earlier in the pipeline. So the practical choice before the next lesson is to take a sample of your documents, run them through a cleaning step, and start looking at what your chunks actually contain. 5 things to carry forward from this lesson. First, clean, well-structured documents are the exception in real projects, not the rule. Build your pipeline assuming the messy case, not the clean one. Second, chunk quality is the ceiling for the entire RAG pipeline. Degraded chunks cannot be recovered by better embeddings or a more capable language model. Third, failure modes cluster into 3 types. Layout failures, where reading order is lost, structure failures, where tables and hierarchies are flattened, and noise injection failures, where boilerplate contaminates content chunks. Fourth, the tools have genuinely improved and are worth using, but they have not solved the hard cases. Multi-column layouts, borderless tables, scanned mixed content documents, and PPTX reading order remain unsolved. Fifth, pre-processing is real engineering work. It belongs in the project plan, the architecture diagram, and the time estimate. Teams that treat it as a quick step before the real work begins are the ones who spend weeks debugging retrieval quality in production. The next lesson covers what to do once your documents are clean, chunking size, overlap, and strategy decisions that determine how well your retrieval system performs.